Idaho is well known around the world for chip production. But here at Micron's Memory R&D Center of Excellence in Boise, it's a different kind of chip that gets all the attention. Behind me is over 200,000 square feet of cutting-edge silicon development, fabrication, and testing facilities. And thanks to Micron's sponsorship, I will be bringing you guys deep under the hood. Not just theoretically, very lithography, much soldering, etc. A key condition of my visit today was that I would be allowed to actually use the equipment and build my own DDR5 memory kit for my next system upgrade. And, well, I'm here, aren't I? So let's go! Oh my goodness. This is a really big parking lot. Boise main site, as it's known, already hosts a small army of high-tech workers, nearly 9,000, and many more are coming as part of a $15 billion investment plan that will see up to 600,000 square feet of sustainable clean room manufacturing space brought online starting in 2025. But its raison d'etre today is completely different. I'm about to enter Fab 4, which contains many of the same incredible etching, polishing, and implantation machines that we saw in our Intel Fab tour. The difference is that not a single wafer that comes out of these multi-million-dollar machines will ever touch the hands of a Micron customer. That's right, this entire Class 100 cleanroom exists for the sole purpose of testing new production techniques that Micron can then deploy at their manufacturing centers in Taiwan, Singapore, Japan, and Virginia. They couldn't even tell me the names of some of the emerging memory technologies that they're validating in here. But what I will tell you is that it's way more advanced than even the high-density 1 beta node DRAM and 232-layer NAND that Micron is currently shipping to customers. What they were able to tell me, though, is that as part of the development of their upcoming 1 gamma and 1 delta nodes, they're currently installing one of ASML's state-of-the-art extreme ultraviolet, or EUV lithography systems. And EUV is absolutely wild. This is worth more than my car, my house, my office, and my life. One of the challenges with EUV is that the wavelength of the light is so small that it gets absorbed by glass. So then, with lenses out of the picture, ASML had to resort to a system of mirrors that are manufactured to literally atomic precision in order to direct the light through the mask. They were giving me some fun speeds and feeds for this boy. Apparently it weighs over 180,000 tons and took 3 747s just to ship all the parts here for it to be assembled. Unbelievable. Now, you might think that with the right equipment, manufacturing RAM is simple, right? I mean, JEDEC creates a specification, and assuming you've got deep enough pockets for ASML's shiniest new toy, you just follow the recipe, right? Well, I asked some Micron folks if that's how it worked, and that's fair enough. I mean, even ignoring the challenges inherent with building something that's never been built before, a lot goes wrong when you're building nanometer-scale features onto silicon, and specialized tools are needed to diagnose these problems. Meet the UF3000 wafer probing machine. This thing is super cool. Our FOUP full of dies comes in here, gets sucked into the machine, aligned via the notch on one side of the wafer, then slid over here under one of these guys. Then, through a combination of machine vision and manual input, these little tiny wires are actually lined up with the individual dies, which can then be tested to ensure that they're functioning as expected. Spoiler alert, a lot of the time they don't. From this screen, I can pick any die I want, anywhere on the wafer, say that one, and the chuck will reposition so that my probes should be exactly above the contact points on that die. We can actually check this by going to image simulation, is that right? And there it is. You can actually see we tested this because there are ever so light contact points from the last time those just running basic tests. You would never set up at a station like this. This is for deep investigations into what's going on with brand new silicon out of the fab. And there are a couple of key benefits to doing it this way. One, you don't tie up an autoprober for hours or days at a time. And two, we're actually able to probe the die even more precisely than with the autoprober. So we just need to look around. Actually, can you guys show me what an individual probe is? Holy crap! Are you flipping kidding me? You guys already saw how small those probes are. These are picoprobe points. These will tell us not just what's happening on the I/O of the die, but what's happening inside of the die. Alright? See this? That's a picoprobe. It looks like a piece of dust on the glass. You're never going to see it, Andrew. You don't stand a chance, my man. And so you guys are expecting me to land this? It seems like you're setting me up to fail. Is that enough? They started moving. Movie magic. We're moving over to one that they already landed for me because they were apparently expecting me to ram the probe into the die, which I did not do, by the way. Anyway, the point is, this is super cool. You can see this one's landed. You can also see the scribe marks that help with machine vision orientation, and that will disappear when swamp, swamp, the space between the die is actually cut away. It's extremely small, okay? My bud here is going to try and land the pico probe. What's really cool is you don't even have to hit probe points with pico probes. You can actually hit individual wires if the wafer has not been passivated yet, which is like a protective layer that goes over top of it. Man, it's amazing how big that probe looks relative to the die. Like, what? Oh, you missed. Yeah. That's fine. I think the people get it. It's really hard. Now, the keen-eyed among you might have noticed that this wafer on the manual probe machine here has been cut in half. That's for good reason. When you're working on early parts, every wafer is precious, and you want as many engineers' eyes on them as possible. So by cutting them in half, you double the number, and so on and so forth. Until finally, as a team, you've managed to find and squash all the bugs, yielding a working wafer from the fab. And here it is. But before we can encapsulate these dies and build them into working memory modules, there are a couple more things we need to do, starting with thinning. You see, this is too thick to build into a working memory die, especially if you're stacking them on top of each other, something Micron is intimately familiar with. So, our first step is to put it in this machine where a thin plastic protective film will be applied to the entire wafer. After that, our wafer gets flipped upside down onto that plastic layer and goes into the grinder. As advertised, it grinds our wafer down to a thickness Micron would not specify for me, but suffice it to say, a lot thinner, and applies it to a blue sticky back piece of plastic just like this one. And the reasons for this are twofold. First of all is the fact that thinned wafers tend to do what they call in Idaho potato chipping, where they curl up like this. And number two is that they need a way to hold all of the individual rectangular dies in place during the slicing process. That takes place in here with saws that have diamond blades that are literally the width of a human hair. I'm not talking a head hair. I'm talking one of the tiny little wimpy end of your finger hair. Probably the most impressive thing about it is how not only does it cut all of our dies perfect on the X and Y axis, it cuts to a perfect depth such that the dies are fully cut and yet still adhered to our sticky back. Once we reach this stage, we're ready for encapsulation or packaging. Now, obviously, let alone solder a wire to them. So packaging is a whole other branch of black magic into itself. They don't do any of it here, unfortunately, but in a nutshell, for a 3D product, you would stack these dies, thermally bond them with incredible precision, attach these bond wires so that you can actually solder the bloody thing to a board, then embed the whole thing in an epoxy or mold compound so that it stays safe, not just in transit, but also during use. You can see this one right here has actually had that mold compound sanded away so that you can see the bare die material. But this familiar plain black rectangle is what's actually going to make its way to the next stage, the characterization tester. Now, up until now, we've gone ahead and we've probed these dies to ensure that they do work as intended, but that's just for show. After encapsulation, we should be left with the familiar black square that looks just like what you'd find on a finished memory module, except that all the testing we've done on it up until now is not sufficient. You see, the issue with our probes is that their long leads are susceptible to signaling interference and crosstalk, which means that they need to be run at a much lower speed than what Micron's customers demand. So while we know that these guys work in theory, we need to plug them into one of these to see if they still work at speed. I'm not going to put it on this one. Do you guys have another one? They dug me up a DDR4 load board that I can't do too much damage to at this point. They also gave me a DDR4 die. Basically, the purpose of this board is to make it much easier to probe all the different pins on the bottom of our packaged die. So we put that little guy in there like that. Then this hold down mechanism clamps it onto the board so that we don't have to solder it and throw these away every time or desolder them or whatever the case may be. The load board then goes onto our testing table here, and man, I'm gonna need an explanation of exactly what it is that is going on with our scopes here. There's obviously a lot more to it, but the basics are that our yellow line is our data strobe, our blue is our clock, and our green and red lines are input and output. And what we want to see is we want to see these lines as vertical as possible. I mean, a theoretical perfect digital signal would actually have flat peaks and valleys and straight lines between them. But in the real world, it takes a little bit of time to go from your low target voltage to your high target voltage, especially when you're operating at speeds in excess of 1 billion cycles per second. Another fun bit is the kind of oscilloscope that you need in order to run this kind of testing is worth a pretty penny. This bad boy will apparently do 33 gigahertz. Now, obviously, Micron's not going to out their suppliers for their exact pricing, but I've been told that this scope, with probes and software and all the other bits and bobs you might need, could be in the neighborhood of $500,000. So to be clear, this is not the kind of thing that they're running at mass production. This is an R&D process where, you know what, this kind of cost, honestly, compared to the equipment it took to make that one decent wafer with a couple usable dies, absolutely dwarfs this. Of course, not every issue can be diagnosed with probing. That is where this X-ray machine comes in. Whether we're looking at an individual die or a full module, this gives us a 3D, non-destructive look at where our problem might lie. All we have to do is load our sample onto this carrier, pop it in here, blast our sample with X-rays, which are captured on this side, while this pedestal slowly rotates, generating, over here, this is made of lead, so very heavy, and be careful, closing that, generating this 3D model that's a composite of all of the individual scans. So this is the PCB under here, this right here is a PMIC module, and this right here is our solder board. And if we look closely, you can see the whole thing. What's really wild though is that's one of the lowest resolution tools in this lab. Behind this door, unfortunately I'm not allowed to open, are scanning electron microscopes that can go down to the gate and transistor level, helping to diagnose any problems in the dies until finally we get maybe 1 or 2 good wafers, at which stage we move to our next station. But while the characterization tester tells us what an experimental design may handle, the DDR6 6000 something, who knows, that doesn't mean that it's ready for prime time. We might have just gotten lucky. So the next step is to go back to the fab and say, let's run a large batch, maybe 100 wafers this time, encapsulate those, and send them over here. This is a binning machine, and it helps Micron's engineers figure out what the variation is with a much larger sample size. I mean, maybe absolutely everything that comes in here runs on target or above, but much more likely, there's going to be some failed dies or other corner cases. So this machine takes in trays of packaged dies and puts them through hell. Intensive operations, hot, cold, the works. Then the dies get sorted according to the engineer's parameters in the outputs down here. Some of these problems might be fixable ones. You know, maybe this bin could be sold as a slower part, or maybe this bin has fuses that you could blow. So you got a 16 gigabit die and, you know, half of it's fine, but you just disable the other half and now it's an 8 gigabit die. That stuff happens all the time. But when it does, that's not a prime die anymore. The dies that go into Micron's consumer Crucial branded DIMMs, those are all going to be prime dies. And on that subject, I think we've actually got some here. So it might be time for me to go build my modules. Now that we have trays upon trays of these packaged dies that will run perfectly at their rated characteristics, I am so excited right now. It is time for us to build some actual modules. Not like that. For that, we're gonna need the machine behind me. This is a multi-stage automated PCB production line, very similar to what Crucial might use to build the server memory modules that are powering the machine that you are watching this video from right now. The first stage is silk screening, which is pretty much the same process that we use to print our t-shirts on lttstore.com, except instead of shirts, we use what I'm informed is called a panel of memory module PCBs, and okay, actually, this part's pretty much the same. So we pop our panel down here, an electronic eye detects that it's correctly placed, then my lovely assistant over here presses the button. Normally, this machine would not operate with the cover open like this, and I have been cautioned to keep my hands well away from it, which I will do. Oh, there it goes. Wow, that's really fast. So you can see that there's kind of a little squeegee that's wiping solder paste shmoo. It's like already done. Wait, is it already coming out the other side? Oh my God, it's going all the way into the other machine already. We didn't even get a chance to look at it. Fortunately, I know what's happening here. This is, oh, not good. We got a defect. This is so cool. I'm so glad we got a defect. This machine creates a 3D model of our panel of memory sticks, and you can see here, everything from two contacts like this, like right here, that would be a big problem, and we saw it our to ones that actually have around 14 little solder pieces, like it looks like all of the curves got converted. Try again, I guess. I'm gonna go and fix it. We can fix it. More than I expected. I've got permission to just open this up. We're just gonna take our soon-to-be modules out. Okay, so there's our. Is this the thing we're looking at here? Must be. Just figuring this out real quick here. Oh yeah, it's good. Given that this is part of the power management of the gym, I pretty much promise you this thing lights on fire and lets out the magic smoke the second you plug it in. Okay, so what do I do now? Unfortunately, I can't show you guys exactly what's going on here. Oh man, I need to. Okay, this is some precision work, and I can't even rest my hand on the rest of the panel. So, okay. I got one of them, I think. Now, you would never do this in mass production, would you? Is this just for like test batches? Thank goodness. Now that I think I fixed the problem, it's entirely possible that A, I didn't, and B, I screwed up something else. So I'm gonna go ahead and load this back on here. See if we nailed it here. Yes, 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 yes. Yes, 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 yes. Not good! Wait, I never actually fixed the ones that were the defects last time. I fixed something else. They apparently thought it was charming how much fun I was having, so they didn't stop me. But this board is bad because of that. That is not something I can fix with an X-Acto knife. Time for round two. I asked about the solder paste they're using, by the way. Even this stuff is cool. It comes out of a refrigerated tube that is surprisingly cold and really, really heavy. They won't tell me exactly what it's made of, but we know for sure it isn't lead. So I'm fairly certain we can eat it without dying. Or at least without dying of lead poisoning anyway. 76 errors this time. Oh boy. Actually, you know what? This might not be that bad. Most of these look like they say insufficient solder, and it's pretty clear they're probably fine. I mean, can I just try? Can I try it? As long as there's no bridges. Okay, so if I fix the bridges, then we can go for it? I mean, the worst case scenario is I make my own defective memory, right? Like, it's not like you guys are shipping it to anyone. Final attempt, and we're going forward no matter what happens here. for a very small component, whereas this is for a large one. And the robot knows what kind of head it has using machine vision and reading these dots on the back. So it's got a little vacuum that allows it to pick up one single part and then place it onto our memory modules. That's why they're more formally known as pick and place machines, although I like my name. That process with the tape loader actually takes a few minutes because there are so many of them. Then, when it's done, we're going to pull the shed from a tray of packaged files, which is loaded over here, and the real good stuff. Now we're ready for the last step, which is basically a fancy pizza oven. There it goes. It's designed to bring our panel up to exactly the perfect temperature, hold it there for a while, then drop it back down, heat it back up, and cool it down. Now, this isn't one of the fancy gravity-defying ones that allows you to pick and place parts on both sides using kind of like a tacky solder paste. You'd be more likely to find something like that on a mass production line. But the test engineers have a pretty cool solution to their single-sided oven. They can actually prepare ahead of time dozens or, wow, actually even hundreds of PCBs that have all the little picky components on one side and then the other side blank. So all they have to do is pick and place these guys, throw them through the oven, and they're this is it. It's cooked. But obviously putting this into a computer is going to be a bit of a problem. So they have a solution for that. It's this little CNC cutter that I have not been briefed on how to use yet, but it couldn't be that hard, right? I mean, everything so far has gone in this way, so surely it goes in head first. And then, oh, well, hopefully I put it in the right way. Okay, so start. I'm getting surprisingly little supervision here, so I'm just doing it. Here we go. Oh, this thing's sick. Get over here, Andrew. Okay, so it goes what? It goes and gets the right cutting tool, or what are we looking at here? It's a board gripper. Ah, so it's got to get the right board gripper. You might be doing SODIMMs or DIMMs or DDR4, DDR5. Okay, here comes my module. Oh, am I too close? That error was caused by one of the safety checks that prevents the wrong profile from running for the kind of memory that you have. So it actually reads the type of modules that are coming in, and if it's got the wrong gripper bit loaded, it's going to say, hey, whoa, 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 you can't do that. But it's really cool that we got that error because it gave us an excuse to open up this machine and take a closer look at it. From the top, it's just a gripper hand. From the bottom, there's actually a router head that cuts off all the extra little tabs, and then the gripper is going to take the finished modules and move them over to that conveyor at the back. Okay, you guys can go ahead and close it. Let's run it. This is cool, by the way. Remember that video that we did on gold recovery from electronics manufacturing back in Taiwan? Well, this is exactly the kind of stuff that would get shipped to them to be broken down and turned back into usable materials. Here they are. And these are ready for my computer at home? No? Oh, right. I don't even know what I've built yet. But before I can find out, we've got one more really important stopover. The long-term burn-in and validation lab. They are constantly building out more capacity because you know what? Theoretically works is not good enough. So Micron is constantly adding more real servers, the exact kind that their customers might put their memory in, and then just absolutely pummeling these things for, we're talking hundreds, thousands upon thousands of hours to see what exactly could possibly go wrong. Ideally nothing, knock on metal. I'm not allowed to tell you how many server racks they have in here, but let's just put it this way. There's a lot of electrical panels, and they're testing a lot more than just current gen. And the same goes for consumer motherboards. On the wall of fame here, they've got validation boards for basically every platform that has ever existed. So that even if years down the line a customer complaint comes through, they can go back to the board maker, the chipset and CPU maker, and work together to figure out who's causing the problem and what the solution might be. What really blew my mind in this room, though, wasn't the environmental chambers or the collection of old motherboards, but rather the collection of weird motherboards, the likes of which I've never seen. Like, the thing is, you think Micron, they probably got to collaborate with brands you think of, like an Intel or an AMD or an Apple. But these days, pretty much everything has a chip in it, and every chip needs RAM. So they also work with brands you might not think of, automotive companies, dishwashers, wild stuff in here, like this thing. We can't show it to you, obviously, but it's 3 times the size of a standard ATX motherboard and absolutely covered in I/O that I have never even heard of. What even is it? Just because it's functional doesn't mean it's pliant. It might seem like Micron is just flexing their sick 3 meter by 3 meter anechoic chamber on me because they know mine is broken. But no, this is an incredibly important part of the development process. So we load our system or our module or our SSD or whatever the case may be onto this turntable, load up an exerciser, which is a program that stresses the component, and the turntable spins around with this antenna here detecting the highest emissions off the product from every direction. This ensures that it meets regulatory requirements and, perhaps more importantly, ensures that it doesn't spew radiation that could cause bit flips or other gremlins to pop up in a given system. Oh, on that subject, by the way, they also intentionally bombard their parts with EMI while monitoring for abnormal behavior or instability, either of which would, of course, be unacceptable. That is one hell of an antenna. You compensating for something? Hilariously, it was a real challenge to find anywhere to test my modules. See, the thing is, DDR5 is very current, and so all the DDR5 capable gear is busy having the crap kicked out of it in one of Micron's testing labs that is chock full of unreleased hardware, so we weren't going to be able to film there. Fortunately, we found a single test bench and a quiet corner that hopefully has working power, where we are going to hook up these modules and see if we can actually post this thing. This is amazing, by the way. People just like set up a test bench for you. I have to set up my own test benches back at the office. They're ridiculous. I still have no idea what we built, but they did tell me they had these guys flown in specially. So maybe there's something pretty cool. K2. Hey! We got something. CPU memory changed. Look at that. We went straight for gold and we got it. Did you guys test these ahead of time? No. We just went for it. Oh, wow. You guys are ballsy. I like it. Uh-oh. We have 96 gig. Wait, what the hell? Am I reading this right? These are 24 gigabyte modules? No one's volunteering. What the hell is a 24 gig module? Explain yourself.
I can't.
That's why nobody volunteered. Okay, so how did... What? Now this is obvious bullshit. 1337 for the part number. 8 terabytes DDR9 9000. That's a missed opportunity. It should have been over 9000, obviously. Okay, but for real, you gotta tell me, you gotta give me something to work with here.
So
and that is why we had to bleep all of that. I really am not allowed to explain this to you guys any further than these are in fact 24 gigabyte memory modules, and am I allowed to run them like in my system? Is there any reason I couldn't? And these are XMP. Oh, bleep that too. All right then. I hope you guys enjoyed this behind the scenes look. I want to give a massive shout out to Micron for making this possible. This is not an easy thing to pull together, and we had a ton of fun, but I don't want to let that distract from the serious work that they're doing here. This wall is all of the 50,000 patents that Micron holds in storage, memory, and associated technologies. This is literally the largest R&D facility for memory and storage products in the Western Hemisphere, and it's pretty clear to me, based on seeing it, that no matter what your budget is, Idaho has everything you need for your next PC, be it a top-of-the-line SSD and memory kit from Crucial, or a literal computer. These stickers are great, but literally everything about them is a lie, from the part number to the fact that it says Crucial on it. That's their consumer brand, and no consumer is ever going to touch these modules. I have been specifically instructed to destroy these if I ever take them out of my computer, because they were not supposed to leave this lab. If you guys enjoyed this video, you might also enjoy our Intel Fab tour, where we went into a little bit more detail about the actual lithography process. That one's also with you.
Mars. A little more effort and victory will be ours. up and victory will be ours. Just a little more effort, and victory will surely be ours.
Victory is near.
Effort and victory will be ours.
It took 121 seconds. A more than 30-year-long, almost spotless safety record, erased within minutes as the Aerospatiale BAC Concorde crashed into a hotel just west of Charles de Gaulle Airport in Paris. But what exactly happened, and during the time leading up to the flight? Using the final report, I will now tell you the story of the beginning of the end of the Concorde. Stay tuned. A huge thank you to CuriosityStream for sponsoring this video. Air France flight 4590 was actually a charter flight. It was scheduled to fly from Charles de Gaulle Airport in Paris, France, over towards JFK International in New York, United States. Once they landed in New York, the passengers, who were mainly German but other nationalities as well, were supposed to get onto a cruise ship that would take them down to Ecuador in South America, making this probably a one-in-a-lifetime trip. There was 100 passengers scheduled for the flight and 6 cabin crew and 3 pilots. The aircraft being flown was the legendary Aerospatiale BAC Concorde, one of the most beautiful aircraft ever constructed and a feat of engineering. The Concorde first flew on the 2nd of March 1969, and during its more than 30-year tenure it had never suffered a fatal accident. There are a couple of things that you need to understand technically about the Concorde in order for this story to make sense. If we start with the design, we all see some passenger delta. But the reason that we here is delta wing. The delta wing will work well both in the subsonic device and the supersonic device. The issue with the delta wing is that in order for it to right up this landing, very high speed and also quite high angle contact. Just to give you an example of the Boeing 737, which generally take off at a speed of around 900 knots. Concorde, on the other hand, is about this. So this is really important because those kind of speeds would stress higher frequency pressure. In fact, Concorde during its 30 years of operation had 57 tire bursts. 12 of those had caused structural issues to the aircraft as pieces of tire had been thrown up toward the underside of the wing. And in 6 cases, the wing tanks had actually penetrated. The most serious of those incidents happened back in 1979, where a Concorde taking off from Washington in the United States had a tire burst during takeoff. Pieces of the tire penetrated the lower part of the wing and one of the wing tanks, causing a small fuel leak, and also it caused damages to the hydraulic system, making it impossible to land the gear. After that incident, a major investigation was launched into the aero test of the Concorde, and a lot of recommendations were made, mainly towards strengthening of tires being used and protection of the hydraulic systems in the landing gear. But there was also some evaluations about the risk of fire. But the investigation team felt that the amount of fuel that could escape from a fuel leak caused by tire debris was relatively small, hence the risk of fire was very small as well. Another thing that you need to understand about the Concorde is that it has a quite complicated fuel system consisting of 13 tanks, 12 of which is housed in the wings and the body of the aircraft, and a 13th tank that is situated towards the very back of the body. And that tank is used as a trim tank where the pilots can transfer fuel into or out of depending on where they want the center of gravity of the aircraft to be, which is really important, especially during takeoff. The engines on the Concorde were 4 Olympus twin-spool turbojet engines that was situated towards the back of the delta wing, just outside and slightly behind the main landing gear. They had variable air intakes in order to be able to fly in supersonic flight, and they also had secondary air intakes on the lower side, slightly behind the main air intakes. And those air intakes are actually going to play a quite important role in this story. All of the 4 engines also were equipped with full reheat or afterburner capability, giving the aircraft a further 18% of thrust during the takeoff. The flight departed on the 25th of July 2000, and already from the start there were some problems. Originally, another Concorde was scheduled to do the flight, but they changed over to this individual during the night. And when the dispatcher started doing the planning for the flight, he realized that there was a technical issue with this Concorde, specifically to one of the thrust reversers. Now, it was not a problem that would keep the aircraft on the ground, but it had a performance penalty, and that performance penalty would potentially lead to a need for a fuel stop on board. On top of that, most of the passengers were German citizens, and they had flown in from Germany earlier, and there had been some kind of problem in the Air France system when it came to checking in both the passengers and the bags. So a lot of the passengers in the bag were actually not on the passenger manifest when the dispatcher started to do the load sheet. He went with this information to the flight crew when they arrived, and the flight crew said that they would take care of the flight planning from that point. The way they did this was they contacted the engineering department at Air France, asked them if they could possibly fix the thrust reverser. They got a positive response on that, and then they proceeded with the pre-flight. Eventually, the passenger discrepancy was thought to be fixed, but they ended up with 19 more bags aboard than what the load manifest would show, giving them a little bit more weight. Around 1400 UTCs, that's 1600 local time in Paris, the flight crew started to do their pre-flight inspections inside the cockpit. Now, the crew flying consisted of a captain. It was a 54-year-old male with 13,477 hours of total time, of which 317 was flown on the Concorde. The captain was scheduled to be the pilot flying for this flight, and the pilot monitoring was going to be the first officer. He was a 50-year-old male with 10,035 hours and 2,698 hours on the Concorde, and he was also a simulator instructor on the Concorde. Joining them on the flight deck was also a very experienced flight engineer. He's 58 years old, male, with 12,532 hours of total time and 937 hours on the Concorde. So this was a very experienced flight crew, which was typical for the Air France Concorde crews, which was a very tight little group consisting of only about 30 pilots. As the flight crew starts preparing the aircraft for flight, the engineer comes back up to them, informing the captain that the thrust reverser is now fully functional, which means that they can upload as much fuel as they need in order to fly directly toward New York, and they settle on a final fuel figure of 95 tons. The crew starts discussing that this is going to bring the aircraft up to a weight which is very close to their maximum structural weight for departure. And when they do the calculation of the performance figures, they settle on a V1 speed of 150 knots, a V rotation speed of 198 knots, and a V2, the ambient out speed of 220 knots. The dispatcher comes in with the final figures for departure, and he tells the crew that he has calculated on a taxi fuel burn of about 2 tons. This is later going to turn out to be way too much, but we'll get to that in a second. At time 14:25, everything is ready for departure. The cabin crew has given cabin secure, all of the passengers are seating down, and the flight crew receives their start clearance. They start up the Concorde engines in sequence 3, 2, and then 4 and 1. And once the startup sequence is complete, they ask for taxi clearance. The runway used in this day is runway 26 right, which is one of the longest runways in Charles de Gaulle. So the air traffic controller asks the Concorde if they are able to take an intersection takeoff. But given their very high weight, the captain instead asks to get full length departure runway 26 right. They receive their taxi clearance, start taxiing down, taxiway Romeo to holding point, runway 26 right, and at time 14:35 UTC, the aircraft starts moving down towards the holding point. As they're taxiing out now, the crew continues with their pre-departure preparation. As part of that, the first officer realizes that one of the electrical control systems for the rudder keeps jumping out of its primary control system into its backup control system. He comments this to the flight engineer. He says, hey, you got the indicators going into green all the time. And the flight engineer responds back to that, yeah, that's true. They discussed this a little bit. They decide to go back into the primary control system anyway. And the flight engineer says that if this problem continues, what happens during the takeoff roll, well, then we'll just ignore it, because this is a dispatchable fault and it's not going to have any impact on the flight. During this taxi out as well, about 4 minutes prior to departure, they initiate a fuel transfer from fuel tank 11, the very back of the aircraft, towards feeder tanks in order to get the center of gravity of the aircraft to 54%, which is the sweet spot for takeoff at maximum takeoff weight. This fuel transfer was successfully completed a few minutes prior to departure. At the same time as this is happening, a DC-10 from Continental Airlines is lining up and taking off from 26 right, the same runway that the Concorde is just about to take off from. During the takeoff roll, a short metal strip, about 43 centimeters, falls off the right-hand engine of the DC-10. There are no indications in the cockpit about this, there's no warnings, and the crew just continues to fly towards the destination. Because this happens only a few minutes prior to the Concorde departure, there are no runway inspections that could pick this up. In fact, in France at the time, there was only mandated 2 runway inspections. There is now taxiing closer to the boarding position on Romeo from 26 right, and the captain was in takeoff briefing. Now this is something that we always tend to do, where we do a little bit of a quick summary of the most important points before we depart. And the captain says, so the takeoff is at maximum takeoff weight, 180 tons, 100. It means 4 readings, maximum M2 of 103, and a failure M2 of 98%. Between 0 and 100 knots, I stop for any oral warning and the tire flash. And the tire flash and the call-out is coming from the right. Between 100 knots and V1, I ignore stop, stop for an engine fire, a tire flash, and a failure result. After V1, we will continue on the standard instrument departure as we just talked about, and will land maximum right. Standard takeoff briefing from the captain. It outlines what the crew are expected to do in case of projected takeoff in the low speed regime, which in this case the Concorde is between 0 knots and 100 knots. It is stop for anything. The gong that they're referring to is what's equivalent to a master caution warning in the Boeing, just a oral warning. Critical failure. And then from 100 knots up to V1, they're a little bit more restricted because they're now in the high speed takeoff. So at that point, they only stop for a fire warning, failure warning, and in this case also what we call a tire flash. A tire flash is a warning light, sudden loss of pressure. Also asked the flight engineer how much fuel they've used during the taxi, because remember, in the load sheet they had 2 tons calculated. The flight engineer responds with, we've got 800 kilos there. So this would indicate that they're actually using about 1 ton less of taxi fuel, and since they were already at the maximum takeoff weight using the 2 ton of taxi fuel that they were supposed to use, if they've used 1 ton less, it means that they're now about 800 kilos above maximum takeoff weight. The flight engineer at this point also says, brake temperature is checked at 150. And the captain asks, is it hotter on the left or the right side? The flight engineer says that it's about the same. And that's going to turn out to be a really important statement for the investigation later on. At time 14:42 UTC, the Concorde was clear to line up and clear for takeoff from a 26 right. Air traffic control gave them the surface wind of 090 degrees at 8 knots, and the pilot had not calculated with that much tailwind in their performance calculations. If they would have seen that their maximum takeoff weight had now been reduced to 180 tons rather than just above 185 tons. The limiting factor here would have been the Concorde's tire speed, because if you take off with tailwind, it's going to bring you up into a higher ground speed before you get enough airspeed to rotate the aircraft. And in this case, the tire speed would have been too high. The later investigation would show that this didn't have a real impact on what happened to this flight. And I also kind of understand it, being a pilot myself. When you line up, there's a lot of things that's happening at the same time. And if you suddenly get a different wind than what you've calculated for, it's easy to miss that, right? But if you're a pilot out there, it is really important actually to take the time and to really think about the wind that you're getting before you start your takeoff roll. From this point onwards, things are going to happen really, really quickly. And this is where the 121 seconds start. At time 14, 42 and 30 seconds, the captain advances the 4 thrust levels in the cockpit towards takeoff thrust. This causes the 4 mighty Olympus engines to roar into full takeoff thrust with full reheat engaged, and the aircraft starts accelerating down the runway. 24 seconds later, the first officer calls out 100, which is then followed by the flight engineer saying 4 greens. This is indicating that each of the 4 go lights that is associated with each engine is showing that the engine is working normally and that the 4 reheats are engaged. 6 seconds later, the first officer calls out V1, and there's now no return from this takeoff. This is about 35 seconds into this flight. At time 14:43 and 9 seconds, a slight yaw to the left is noted on the flight data recorder. This yaw was not caused by any rudder movement, and at this point, when the aircraft passed about 1,700 meters of the runway, they also found pieces of the water deflector from the left-hand main gear. So this probably represented a time when the Concorde rolled over that metal strip that was left behind by the DC-10 that had departed earlier. Within half a second, noise is recorded on the cockpit voice recorder, and that's likely coming from the explosion of one of the tires on the left main gear bogie. The reason that the investigators thought so was because at this point on the runway, they could find the metal strip and also pieces of tire debris. 1 second later, the aircraft has accelerated to a speed of 178 knots, and at this point, that's about 1,810 meters into the